Okay, so folks, in this sequence of pre-works, we're going to be looking at our properties of exponents, and we're going to start out at the very basic and then start building up as we go. I find that often students have are missing some pieces of their knowledge of exponents, and that really comes back to bite them. In fact, I say here that properties of exponents is probably the most important skill for students to have a strong grasp of when moving into calculus. I see it a lot of times where students struggle, not because of the calculus, but because they don't have these properties of exponents down solid. So suppose we've got a real number a and a natural number n. So that's this notation right here just means that a is any real number, and that means a number found on the number line, and that n is a natural number. So the natural numbers are not real numbers, or not the real numbers, they're a subset of them. The natural numbers are the ones that we count with, 1, 2, 3, etc. Some people may say we include 0. I'm choosing not to. So we're saying pick any real number and a natural number. I want to define what we mean by a to the n. A to the n is just a shorthand notation for a multiplied to itself n times. So we'd have a times a times a dot 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 times a, and we're going to do this n times. So the example that would maybe go with that is if we were to take 2 to the third power, that means to take 2 and to multiply it by itself 3 times, which we could simplify to 8. Usually then we will skip that middle step and we will just abbreviate that as 2 to the third equals 8. Okay. So with this one definition plus our knowledge of multiplication, we can actually develop a whole bunch of properties. So the first property I want to look at is that if we take a to the n times a to the m, this is equal to a to the n plus m. Now I'd like to motivate this definition for you. So let's look at this example before we actually do a computation. Let's look at this example here. If I took 2 to the third times 2 to the fourth, that would be equal to, by definition, 2 times 2 times 2. And we're going to multiply that to 2 to the fourth, which is 2 times 2 times 2 times 2. And if we were to simplify this, notice that these parentheses are no longer lending any information. And we've got 2 multiplied to itself once, twice, 3 times, 4 times, 5 times, 6 times, 7 times. And so that's equal to 2 to the 7th. Now, it's this example that I just did right here that I think that a lot of students are missing. Some students have these facts memorized, but they don't quite know where they come from. So it's very important that you truly and kind of in your bones know these properties of exponents, why they are true. So let's just look at a simple example. If I were to take x to the third times y squared times x to the fifth, this property says that I can rewrite this, let's just reorder this as x to the third times x to the eighth times y squared. That says I can rewrite that as x to the 11th times y squared. So we combine the exponents here through addition. I want to point out that y squared, y is not of the same base. Notice that this property said that we had to have the same base. Okay, let's keep going. So the next property that I would like to look at is if we took a to the n and we raised that to the mth power. That's equal to a to the n times m. So again, I think it's very important that you not think of that as something that you just memorize. You should instinctively know why that's true, and the best way to do it is to give yourself a concrete example. So for example here, if I were to take a to the or 2 to the third and then raise that to the second power, that means to take 2 to the third times 2 to the third, but that just means to do 2 times 2 times 2 times 2 times 2 times 2, where those first 3 factors came from the first expression and the second 3 factors came from the second, and that gives me 2 to the 6th power. So what we notice is after you've done this a few times, you don't want to write this out ever again. You just want to skip all this middle work here and jump straight to the fact that 2 to the third squared is 2 to the 6th, and that's what this property is allowing you to do, or telling you that you're allowed to do. So let's look at this example here. If we were to take x squared to the third power times y to the fifth times x to the sixth, we could clean this up as x to the sixth, y to the fifth, x to the sixth. which would give me x to the 12th, incorporating the earlier property, y to the 5th. Okay. Let's keep going, folks. The next property tells us that if we were to take a times b to the n, that's equal to a to the n, b to the n. So that is exponents distribute over multiplication. Now, this is the property that I see most often incorrectly applied by students. A lot of students think then that this property applies to this expression here, and this does not equal a to the n plus b to the n. So exponents do not distribute over addition. Exponents do distribute over multiplication. The operation here is multiplication, so exponents distribute over them. Here the operation is addition. Exponents do not distribute over addition. So be very careful in applying that property. What I would encourage you to do is to convince yourself of that. If you were to take, let's say, just 2 to the x cubed, that's equal to 2 times 2 times 2. Excuse me, let me that is true, but let's set it up this way. It means to take 2x times 2x times 2x, which is equal to, reordering through multiplication, 2 times 2 times 2 times x times x times x, and so that's where we get 2 to the third x cubed, which you could also write as 8x cubed. But here we're saying never again do we want to write out 2x cubed as 2x times 2x times 2x, and then write it out this way and then collect it. We'll just go ahead and distribute the exponent over, careful, what's that operation there? Multiplication. Okay. So let's just do an example of that. If we were to have x squared y to the third, all raised to the 4th power, that's equal to x squared to the 4th power, y cubed, excuse me, that's a little sloppy, y cubed to the 4th power, and those both simplify by earlier properties to x to the 8th, y to the 12th. Notice oftentimes you are doing multiple properties at once. The last property that I'd like to talk about is if we have a to the n divided by a to the m, that's equal to a to the n minus m. And to convince you of that, let's look at 2 to the 5th divided by 2 cubed. Well, 2 to the 5th, just by definition, is 2 multiplied to itself 5 times. And 2 cubed, by definition, is this. And then we can divide out like factors or cancel out like factors. And so we end up with this expression here, which is just equal to 2 to the 2nd. And the property is noticing that if I were to take 5 minus 3, I would get to that exponent of 2. And that's what that property shortcuts. So let's look at an example of that. If we were to do, say, y to the 9th divided by y, let's see here, divided by x y to the 7th, that would be equal to y squared all over x, right? Simplified by saying that I have y to the 9th divided by y to the 7th. That would be the same thing as 9 factors of y in the numerator, 7 factors of y in the denominator. After dividing out like factors, we're just left with 2 factors of y upstairs. So folks, all of the above properties were developed for n being a natural number. Remember, we use that symbol, that n, that stands for the natural numbers. So notice that in all of these examples that I gave you, all of my exponents in the concrete examples, all of those were nice natural numbers. We didn't use negative numbers, we didn't use 0, we didn't use fractions, we didn't use irrational numbers. So it turns out that if we define everything correctly, we can force the same properties to hold for the expression a to the b, where b is not necessarily a natural number, but any real number. Okay? But it's important to realize that once you do that, this original definition of saying what's a to the n, it's a multiplied to itself n times, no longer applies. Just to motivate that, so make sure you understand what I just said there, folks, if I were to take a to the 3/5, that does not mean to multiply a by itself 3/5 times. That doesn't even make sense. So we're going to have to give definitions for when the exponent is not a natural number. It's not one of the numbers that we listed up here, 3, 2, 7, 6, etc., when they're not natural numbers. So we won't do all of that today, but we'll do a little bit. Let's get started. If we were to take a to the 0, we are going to define this. So this does not fit the mold. This doesn't fit the mold of what I just explained up here, but we're going to define a to the 0 to be the number 1. So you don't try to rationalize that to yourself. You don't say, wait, why is that so? It's not why is that so, it's we chose to define it this way so that we can continue to carry over the properties that we were just looking at. Okay? So yes, it doesn't make sense to say multiply a to itself 0 times, but that's not what I'm saying. We're defining this. This is definition. We chose to define it this way. Okay? Likewise, if we have, for a real number a and a natural number n, if I want to talk about a to the minus n, we define this to be 1 over a to the n. Okay? Let's look at a concrete example of that. If I were to look at 3 to the minus 2 power, by definition, not by explaining, not by saying multiply 3 to itself negative 2 times, that doesn't hold any longer. We're defining 3 to the minus 2 to be 1 over 3 squared, which is equal to 1/9. Folks, that footnote's not particularly important because we've already kind of moved past that. So let's look at a couple of examples here. If we take 3 to the minus 4, that's 1 over 3 to the 4th, which is equal to 1 over... I have a hard time with that, folks. I don't know what 3 to the 4th is, but I do know that that's the same thing as 3 squared times 3 squared, and I know that's 1 over 9 times 9, and so that gives me 1 over 81. Let's look at this fraction right here. We're going to develop a property for this in a moment, but let's just look at this right here. Right now, what does it mean to take 1/3 to the negative 2 power? It means to take 1 over 1/3 to the second power. How do I take 1/3 to the second power? I'm going to multiply 1/3 by itself, and so that gives me 1 over 1/9, and I could simplify that to be 9 when I multiply by the reciprocal. Now, if you knew another way to do this problem, that's great. We're going to talk about that property in just a second here. But for right now, what does it mean to raise something to the negative 2 power? It means to take 1 over that expression to the positive 2 power, which is now back in terms of something that we now understand. Okay? So let's practice this one here, folks. There's a lot going on in this problem. So let's see here. We've got 5 to the 0 times 5 to the 4th times 5 divided by 5 cubed. I'm just recopying it. You don't have to do this. 5 cubed times 5 to the minus 8. So simplifying each one of these terms, 5 to the 0 is 1. My numerator here is 5 to the 6th over 5 cubed. This simplifies to be 5 to the 9th because we're raising an exponent to a power, so we multiply. And I'll write this as 1 over 5 to the 8th. We don't need to multiply by that factor of 1. That's just the original expression. I'm going to simplify. There's lots of ways to simplify this, folks. In fact, that's one of the difficulties of working with exponents is you may be thinking of simplifying it one way using one sequence of properties, and your teacher might be thinking of simplifying it another way using a different sequence of properties, and you might think that you're not understanding it, but it's just another way of doing it. So there's many ways to do this. I'm going to go ahead and drop off that factor of 1. 5 to the 6th divided by 5 cubed by my subtraction property would be 5 to the 3rd because 6 minus 3 is 3 times 5 to the 9th times 1 over 5 to the 8th. But how do you multiply by that fraction? It would just be 5 to the 8th here. So that gives us 5 to the 12th in the numerator over 5 to the 8th, which simplifies to be 5 to the 4th power, which I happen to know is 625, although you could compute that if you wanted to. Okay, folks, the last thing I want to do in this video is I want to motivate why we chose a to the 0 to be 1 and why we chose a to the minus n to be 1 over a to the n. And hopefully that gives you some insight, but I want to reiterate because I see students make this mistake all the time. They all remember this rule. What does it mean to take a cubed? It means to multiply a by itself 3 times. They remember that rule, and they're trying to apply that rule when our exponents are 0, or when our exponents are negative 2, or when our exponents are 3/2, and that rule no longer applies. We give separate definitions when our exponent is not a natural number. Okay? But I want to motivate, why did we choose to define it this way? And this is not the definition, but this helps with the motivation. If I were to take 3 to the 4th power, turns out that I think we just did that was 81. If I took 3 cubed, that's 27. If I take 3 squared, that's equal to 9. If I take 3 to the 1st, that's just equal to 3. And what we notice is that each time when I step down by 1 power, it's as if I took this expression and divided by 3. When I went from 3 to the 4th to 3 to the 3rd, this new number, 27, is 81 divided by 3. Likewise, when I went from 3 to the 3rd to 3 to the 2nd, it's as if I took this 27 and divided it by 3. When I went from 3 to the 2nd to 3 to the 1st, it's like I took 9 and divided by 3. And so, this is just to motivate our definition. If I were to talk about 3 to the 0, it would be as if I took 3 and divided it by 3, which is 1. Or if I were to talk about 3 to the minus 1, it would be as if I took 3 to the 0, which is 1, and divided that by 3, giving me 1/3. If I were to take 3 to the minus 2, that would be the same thing as 1/9. Okay, so folks, we'll do a couple more properties of exponents, and then I'll leave you to work some problems, and we'll do all that in the next video, so I'll see you there.